Hi everyone and welcome. In this video tutorial I would like to show you how to use PyTorch. So for this I'd like to demonstrate how to install PyTorch on a target system. Right now I'm on a Mac and what I'm going to do is to switch over to a Linux computer. So for this I'm using SSH, which allows me to connect to a distal computer. So I'm connected to a computer which is called Oak here, and right now I'm actually running on the Linux computer system. So this is a terminal on the Linux computer system. What I'm going to demonstrate right now is how to create a virtual environment so that we can install the packages that we need for the course. And I'm then going to install Python 3.9 and then the library which is called PyTorch. So I will demonstrate this on a Linux target system. If you have a Mac, you can do pretty much the same because Mac runs on Unix, which is very similar to Linux. And if you have a Windows, I'm not sure how to do this. I don't have a Windows computer, but I know that this is possible to have a virtual Linux environment in your Windows. And maybe this is the best option so that you can follow along with a similar system as mine. So here we go. We start with using Conda. The way you have Conda is by installing either Mini Conda or Anaconda. Either works fine. I have Mini Conda, for instance. Once Conda is installed, you can use it with the command conda create, and then you specify the name of the environment you want to create. So we're going to say that this is CSB1021 and the Python version that you want to use. So we're going to say Python equals 3.9. If you install another version, everything should be fine, but 3.9 is just a good version in the sense that this is not too recent, so it has many packages available, and it's not too old, meaning that it has many of the nice features of the recent versions of Python. So you press enter, and this step can take a little while. So when you're on that screen here, you just need to press enter. The default is yes. This will install all the packages that are shown here. Okay, once this is done, you have the indication that you can use conda activate and then the name of the environment to have access to what you just created. So here we go, conda activate CSB1021. And so nothing changes in appearance, but now if I start Python, I have version 3.9. So what conda does is that it separates this particular version of Python from the rest of your system. This is very handy for teaching because then we can have exactly the target that we want in terms of the versions of Python, the versions of PyTorch, and other packages. So this is all we wanted to check. We can then exit the Python console. And now we are ready to install PyTorch. So before installing PyTorch, make sure that you have this conda environment which is active with the command conda activate CSB1021. And then the command to install PyTorch is pip install, and the name of the package is torch, not PyTorch. So you just go ahead and say pip install torch and press enter. That will download and install a couple of packages. Okay, this is good. PyTorch has been installed. So we are now ready to test installation. So I restart Python and I say import torch. So you can see here that I immediately start with an issue. So it works, but I get a warning that NumPy is not installed. So NumPy is a very important computational library in Python. So it's a good idea to have NumPy installed when you use PyTorch. So here we go again. I exit Python and I'm ready to install NumPy with the same command, pip install NumPy. Now we can try again the installation to make sure that things work fine. So Python import torch. And now this works without warning. So I have everything I need to be able to use PyTorch. So at that stage here, if you manage to get that far, then you have managed to make a complete installation of PyTorch on your computer. One thing that is really nice about PyTorch, but which is optional, is to see whether we have access to the graphical acceleration, to the GPU acceleration. So PyTorch is a really nice system because it allows us to talk directly to the graphics card if we have one, and we can get very spectacular speed up sometimes if we have access to this. So one way to check if you have access to your GPU is to type torch CUDA is underscore available. And so here it says true, which means that with this default installation, I am already able to use a GPU acceleration. If on your system it says false, it's okay. It's not a problem at all. It just means that the code is going to run a little bit slower at times. But maybe we'll see how to use GPU acceleration for everybody later in the semester. At that point, that's all we need. We have a running installation of PyTorch. Now that we have a running installation of PyTorch, we restart a new session. So we start Python and import torch. That always takes a few seconds. Now we're going to give a little primer on the basic element of PyTorch, which are the tensors. So a tensor, you can think of it as a vector, a matrix, or a multi-dimensional array. So one way to create tensors in PyTorch is to use the construct torch.tensor, written like this, and between the round brackets you put the element that you want to be in the tensor. So for instance 1, 2, 3, and we say that this here would be a tensor x here. So now when I enter x, I see that this is a tensor with elements 1, 2, 3. So that here is in a sense a vector, that it has a dimension 3, but importantly all the 3 elements are on a single line. I can create a tensor which is a 2D array instead. So one way to do this is to say that, for example, tensor y here is going to be 1, 2, 3, and then 4, 5, 6, but I need to wrap it into another pair of square brackets like this here. So with this, y appears as a 2D array with 6 dimensions, which are 2 by 3. So the essential concept of PyTorch and the tensor is the concept of the shape of a tensor. So we can ask the shape of a tensor with the construct x.shape. So that shows me that x here has dimension 3, and that corresponds to the fact that it has 3 elements on a single row. The shape of y here is 2, 3. So it says that the first dimension is 2 here, so it has 2 rows, and the second dimension is 3. It has 3 columns, and in total 6 elements. So the shape of a tensor, you can think of it as the dimensions of a matrix in a way, but there's no limit to the number of dimensions of a tensor. It doesn't have to be only 2D. It can be actually pretty much anything we want. So for instance, we're going to create a tensor Z that has 3 dimensions. So one way to do this is to now continue with the same logic. So we separate here the 2 elements that were present, the 2 rows that were present, by adding another 2 rows of numbers here. So 7, 8, 9, and then 10, 11, 12. And again, we need to wrap them into these square brackets. And again, if I want to say that there is yet another dimension, I need to wrap this all into yet another pair of square brackets like that. And now if I say z.shape, I get the fact that z has 2 by 2 by 3 dimensions. And if I press Z and enter, I get a representation that looks like this. It's showed as a superposition of 2 matrices, of 2 2D arrays. So we have seen examples where x had dimension 3, y had dimension 2 by 3, and z has dimension 2 by 2 by 3. An essential aspect of tensors is that we can perform all sorts of mathematical operations with them. So for instance, if I want to multiply all the elements of x by 2, I just have to do 2 times, using the star here, x, and you can see that I get 2, 4, 6. Like these two here has been applied to all the elements of x. And so this works for pretty much all the mathematical operations. If I want to raise x to the power 2, for instance, I can do x times x. And so I get 149. So you can see that I get a compact way of representing operations that apply to all the elements of a tensor. This is called vectorized computing. And this is not only more compact, this is also much faster. So we cannot measure it here because these operations are almost instantaneous. But when we have a large amount of calculations to perform, this makes a really big difference if we can perform them on tensors versus on numbers or lists. We can also perform operations that combine multiple tensors. So for example, we can do x plus y here. It's interesting that the result actually works because x and y have different dimensions. So x has dimension 3 and y has dimension 2 by 3. And the result is a 2 by 3 tensor that is here. If we look carefully at the definition of x and y, we can see that this 1, 2, 3 here of x has been applied first to the first row of y here, and second to the second row of y. 4, 5, 6 becomes 5, 7, 9. So in this particular case, we see that PyTorch was happy to do the additions of two tensors that do not have the same shape. But in general, this won't always work. This works in this case because the rightmost dimension of x, which is 3, is the same as the rightmost dimensions of y, which is also 3. And so PyTorch guesses that it can just double the tensor x in order to match the dimension of y. This is called broadcasting. So when broadcasting works, it's pretty powerful, but it does not work all the time. To give a more concrete example, let's see that if we define x this time as a tensor which has dimension 2, so we say 1 and 2, here, when we try to perform x plus y, we can see that we get an error. In this particular case, PyTorch will not want to do the addition of x and y because they do not have the same rightmost dimensions. So as long as the tensors have got the same rightmost dimension or rightmost dimensions, usually PyTorch will be okay to broadcast the smaller one to match the bigger one. But if there's no way to do this, then this will just return an error and PyTorch will refuse to do the operation. So one important aspect of PyTorch is that it comes with a large array of probability distributions. So they are going to be very useful for us in this course. We're going to demonstrate a couple of them and to show how to use them. The first we're going to demonstrate is the Bernoulli distribution. So the way to use it is to start with first torch.Bernoulli in small letters, and within the function Bernoulli, we need to pass the parameters of the Bernoulli distribution. Remember, the Bernoulli distribution is the one where you flip a coin and you have a certain probability that it lands heads or tail. So we need to specify the probability that each coin lands either heads or tail. Let's say we're working with the probability of landing heads. So we specify these probabilities in the form of a tensor. So we would say torch, tensor, and then we specify these probabilities individually. We would say that the first coin has a 50-50 probability of landing heads. The second would have only 5% chance of landing head, and the third would have a 95% chance of landing head. So the call looks like this, and once we press enter, we get an outcome of the Bernoulli distribution. If we repeat the call, we may get a different output. Here we get the same because the second and the third are of course, very much biased towards 0 and 1. And this one here is fairly random, the first coin. So we see that when we repeat the call multiple times, we get a lot of variation on the first coin, but we do not get a lot of variation on the second and on the third coin. Another distribution that is quite handy and that we will use quite often is the standard uniform distribution. So the call for this uniform distribution is torch.rand, just random. And it doesn't work the same way as the Bernoulli distribution. In this case, we need to specify how many random numbers we want to get. Let's say 3. If I do just torch.rand3, I get 3 random numbers between 0 and 1. What's interesting about functions that are called this way is that we do not need to specify an integer here. We can specify multiple dimensions, and in principle, we now get a tensor with as many dimensions as the one that we requested when we called torch.rand. So in this case, we have a 2D array with 3 rows and 2 columns. All of them are filled with random numbers between 0 and 1. So this here, torch.rand function, is fairly useful as well. Another function that works on the similar pattern as torch.rand, and that is sometimes confused with torch.rand, is the Gaussian distribution, because it's called with torch.randn, and that stands for random normal. So this is here the Gaussian distribution. It works on the same pattern, so if I ask 3 random Gaussian numbers, I get 3 numbers here which have no minimum, no maximum, but they're distributed with an average of 0 and a standard deviation of 1, which means that I'm extremely unlikely to see values that are, let's say, below -5 or above 5. And it's the same principle here. If I say torch.rand3, 2, I get a 2D array of Gaussian random numbers with 3 rows and 2 columns. So that's a handy way where I can get standard Gaussian random numbers very easily using PyTorch. Those are just some of the ways that we can generate random numbers here at the terminal, but PyTorch has, of course, many more options, and we will see a bit later in the course that it also has another interface to define proper distributions. Here, this is rather just a hack to generate some random numbers on demand when we need. One little trick, which will be handy at times, is to set the random generator of PyTorch. So this will allow us to generate exactly the same randomness. So one way to do this is to use the command torch.manual_seed, and then you can put the number you like. So for me, my favorite number is 123. This is the way I usually initialize the random generator. So when you press enter, you see that this returns a weird output here, but you can ignore that. The point is that once you have fixed the random generator, this makes a deterministic random function. Now, when I call torch.randn, I get, let's say, these numbers that are here. And if I call again the manual seed123, and I call again the same random function, I can see that the numbers are identical. And if you have PyTorch installed on your computer, you can do the same. You can say torch.manualseed123 and run that exact command, and you should get exactly the same output here. So this is a handy way so that we can exchange randomness between participants. That's very useful sometimes for debugging, for instance. But the reason why people use PyTorch is not because it has cool tensors or because it can create random numbers. It's because it has automatic differentiation. So we are now going to exemplify how this works with just one simple example, and we're also going to see why this is interesting to have this. So when I create a vector or a tensor, I can say, for example, that x is a tensor that contains only one number, let's say 1, so I would create it with torch.tensor, and then I have to create the number 1 between brackets here, but I can also add one additional parameter in the constructor that says requires _grad equals true. So now when I enter x here, I have the value of the tensor, but also the fact that this has a gradient attached to it. So we're going to see in a minute what that means, that it has a gradient attached to it. For this, we're going to create a function of the variable x that is quite simple. So using the standard Python language, we create here a function with def f of x, and we say that it returns, let's say, the exponential of x that we're going to write as torch.exp of x. That's the way you create an exponential out of a tensor, plus x squared that we're going to write x times x. So now if I call f of x on the variable that I have here, the value is 1, then I get the value of the function, which is 3.71 and something, and it says that there is a grad function which is called add backward 0. So this is not important here. This just says that we have the capacity to measure the gradient or the derivative on the parameter x here. And this is fairly simple to do. We just need to do f of x, and then this is a tensor with a grad function, so I can call the function backward here. This is a function that just computes the derivative. When I press enter, it takes a while and nothing happens. But if I say x.grad here, I've got a value which is equal to 4.7183. And so if you manually compute the derivative of the function f at the value 1, you will see that this is actually equal to that here. So this is the correct derivative of the function. So the first thing is that we see that PyTorch makes it relatively simple to define an arbitrary function here, and then to compute the derivative or the gradient at one particular point. We have taken an extremely simple example here with only one number, but you could do the same with much more complex functions with hundreds or even millions of variables, and it would compute the gradient just the same. An even more interesting feature of PyTorch is the fact that using these derivatives, we can do what is called gradient descent, stochastic gradient descent or gradient descent. So this allows us to optimize the functions without having to go into very complex details about functional optimization. So all we need to do for this is to create an optimizer. So the way to do this is that we say opt for optimizer is equal to torch.optim dot, and then we choose the optimizer that we're interested in. For example, I'm going to say that I want to use a very simple optimizer which is called SGD for stochastic gradient descent here. I could use something else like Atom or Atom W. There are many other optimizers. This one is one of the least efficient, but this is also one of the most simple and the most robust. So for the sake of just giving an example, we're going to stick with this one. And then I need to specify which are the parameters that I want to optimize. So here I have to say that the parameter I'm interested in is x, and I have to put it inside something that can be iterated over, like a list, for example, a Python list. And then we need to specify a learning rate. We're going to say that 0.1 is as good a number as any for the learning rate. So that here defines an optimizer which will allow me to find the value of x, which minimizes the function f. So for this, I need to call the function opt step, and by default, this will optimize all the variables that we have put inside the optimizer here. So just this, and if we now look at the new value of x, we can see that this is no longer equal to 1. So 1 was too big a value to minimize f, so it's been reduced to 0.5282. So that is one step of optimization of finding the minimum of f. And so from here the logic is simple. We can repeat the same operation multiple times until we find that x converges to a value where the gradient is 0. We're just going to go down the gradient and then find the value of x that minimizes f. So each cycle we need to do the same. We need to remove all the gradient information that we have accumulated so far. So that's opt.0_grad. This here removes the gradient information that we had about x. And then we need to compute the derivative again, which we do with f of x backward. We then do the gradient step here, which reduces or increases the value of x depending on what needs to be done so as to get closer to the minimum. And while we're at it, we're going to print the value of x after it has been updated here. So we see that x is further reduced here, and we repeat the process again and again. We erase the gradient, compute the derivative, update x, and print it. And we do this again and again until we have some convergence. So that's it. We see that at some point we start to slow down around a value of x which is minus 0.3517. The true value is probably a bit lower than this because it seems that we're going down all the time. But this is quite interesting because we now have an idea of which is the value of x that minimizes the function. And we have done pretty much no calculation whatsoever for this. This was all made automatically using the library that we're using, so PyTorch, the fact that it can do standard differentiation here, and the fact that it can compute relatively complex functions like the exponential, the square, and of course many others. So here I'd like to mention that the name of the optimizer is called SGD for stochastic gradient descent, but in that particular case there is no stochasticity at all. This is a completely deterministic algorithm. The fact that this is called stochastic means that it works even if you take a subsample, a stochastic or random subsample of the data. But in this particular case, it is actually a deterministic algorithm. So we have seen how using an optimizer, we can optimize a function, we can minimize it by doing cycles of differentiation here using backward, and then running the step of the optimizer. This is the essence of gradient descent here. So calculating the derivative or the gradient each step, and then moving along that gradient until this gradient is completely flat. So this here concludes our quick tour of PyTorch.